all the data will be in ones and zeros. Even if one bit, suppose you want to convert the representation from BCD to XS3, what are the steps you can follow is, if number of ones is odd, then parity bit will be 0. That means how to convert a binary coded decimal number. I'm Saumeshri, Dr. Saumeshri, Department of Computer Science, Vidhyaashram College. Welcome to the next session of Digital Electronics. In the last session, I talk about some of the binary codes that are used in digital devices like binary coded decimal or XS3 code or gray code. Apart from all these types, we have another type of code which does not do anything with the number generation or number display in the devices, but the codes are used for detecting the errors in the incoming data. Like if you have any attacker or if somebody hacks the data that is coming over the network, it may be changed. The form of message or the message in which it is sent, the normal message have been changed or may be changed, but the receiver may not be able to recognize the error if you don't have any method to detect that, because all the data will be in ones and zeros. Even if one bit changes from 0 to 1, there may be a change in the data, entire data, when it is converted to the high level language. Because of this intention, there is a necessity of some method where the receiver will be able to recognize that there is a mistake or there is a received data which is not in a proper form, which was sent by the sender. How do you recognize these methods, or how do you recognize these mistakes or errors? Is using certain methods. What are those methods is, if you want to get something delivered to a person, what you will add is, you will add an address, is it not? If you don't have an address, you cannot deliver the product to the receiver, to the person, is it not? But in the same way, we have some other method in digital devices to detect any error which has been sent by the sender. For this purpose, we have the error detection codes, because everything must be in digital form, in binary form. Even the error detecting method is also using the same form of binary to detect the errors. How does it is going to detect the error in a data? Let's have a look at that in the present session. Okay. Now we have the error detection codes. Why do you need error detection codes? What is the necessity of these error detection codes is, these are sequence of numbers. As I said, binary doesn't contain anything other than zeros and ones. That means this error detecting code must also be in the binary form only, where we have a sequence of numbers, any sequence, which are generated in a particular procedure. You cannot randomly generate anything to detect an error. You have to have a determined method, predetermined method to detect an error. Okay. Error detecting codes serves the same purpose, having a predetermined procedure to identify an error that may have encountered or that may have generated while passing through the network, isn't it? Next, when these bits or data are transmitted, there may be the chances of data are corrupted. They may be corrupted. Even a single bit change may change the form of the data. Because of this, we need a particular method to identify the error. These error detecting codes will ensure that the messages that are received by the receiver will be out of the errors. That means they'll receive the data in the same form which was sent by a sender. Okay. Here, one method of encoding or decoding may be used. Encoding is hiding that or changing the normal form so that outsiders, unauthorized person will not be able to recognize the data, which is called as encoding. When it is sent as an encoded form at the receiver, you cannot expect that he has to recognize the data in the encoded form only. That means you need to have a decoding method also. That means to hide or to change the form of the message from original to hidden form, and when it is received, it must be changed to normal form by the hidden form. All these things, along with that, error detection must also be done. Okay. For this, we have some of the methods that can be followed in digital devices, which helps the receiver to identify any error. Okay. These error detecting codes are adopted for backward error correction. What is backward error correction is, the receiver sends a feedback message. Backward messages, forwarded is forwarded messages given by a sender and is received by a receiver. Backward message is like an acknowledgement. When receiver receives the message, he will send an acknowledgement saying that the message is in a proper form or it is in the same form as is sent by the sender. This is called as the backward error correction technique, where a feedback message is sent to the sender to inform whether there is a message, whether the received message is in normal form or received as it is, or is there any error. Okay. If there are errors, if the error is existing, what does the receiver will do is, he'll simply discard the received message and sends the acknowledgement that there is an error generated in the message. What does the sender must do is, he has to retransmit the message until the receiver gets the normal message or the correct form of message. Okay. These error detecting codes are usually block codes where the messages are divided into fixed blocks. In network, you cannot send the data as it is. If you have one file or a document, it will not be sent as a single file. Instead, for easing the method of error detection as well as speed in the passing of the message from the sender to receiver, the entire data is divided into packets with certain bits, specific bits, so that it will be easier to implement any error detecting technique over each of the packet of the data. Like we send pieces of paper and has been combined to form the entire page. Like that, data will be divided into several chunks and will be loaded over the network or sent over the network, so that when it is received with the receiver system, it will be reorganized or it will be organized to get the normal form of the data. Okay. So, for this fixed block of bits, several methods or techniques are implemented to make the error detection easier. Okay. This also involves error detection, whether any error occurred in the message or not, what type of error may have occurred. Okay. using the number of error bits that are added to the different data packets. Alright. In this error detection techniques, we have mainly three types. One is checking the parity of the message. Another is generating a checksum. The third one is checking for the cyclic redundancy check bits or CRC. It is generally called as CRC, cyclic redundancy check method. CRC method will generate a bit. Checksum method will generate another bit, whereas parity bit also generates another bit. Alright, let's have a glance about these three methods. First comes is the parity check. What is this parity check? What it is going to do is, this can be implemented by adding one extra bit, okay, so that it will help you to detect the error. Adding an extra bit, whether it is 1 or 0, which bit we are going to add is, if you add 0, there will not be any much benefit of adding 0 to the data packet. Instead, what does the technique will do is, it will add the 1 in a particular number so that it will be easier for the receiver to recognize the error or detect the error. Okay. While creating a frame, when you create a frame, the sender counts the number of ones, okay, in the frame. Suppose if you have this message to be passed, if this is the message, I may make it packets of 4 bits. If I make it a packet of 4 bits, what does the error detection technique will implement is, it will count the number of ones in each of the packet frame. How many numbers are there? 1. In this group, you have 3 ones. In this, we have 2 ones. Again, this frame or packet, data packet has 2 frames. What is the benefit of using this method? How do we implement the parity bit method using the number of ones is, you can have 2 methods or 2 techniques to implement this parity bit. One is even parity, another one is odd parity. What is the even parity, or how does the even parity and odd parity differentiates is, in even parity, it checks for the number of ones, okay. In both the methods, the number of ones is counted. What happens in even parity, if you have implemented even parity technique, if number of ones is even, in a frame, if number of ones is even, the parity bit is set to 0. Parity bit will be set to 0. If the number of ones is odd, if I have taken even parity, okay, number of ones is even. In this frame, number of ones is 2. So, the parity bit will be set to 0. Okay, it will be added with this frame. Parity bit, there will be one memory location fixed for parity bit. A 0 may be added with this frame to identify that you have 2 ones in this frame. Suppose again the second frame in this example have again even number of ones, 1 and 2. Again this will have an extra parity bit which is set to 0. Whereas in third frame we have odd number of ones. Since this is even bit, a 1 is added. If the number of ones is odd, then the parity value will be set to 1. That means here now we have 0, 1, 0, 0, 1, which will be a single frame. Again we have 0, 1, 0, 1, 0. and the third frame will be 0, 1, 1, 1, 0. We have 3 frames. This is 1. Since it is having odd number of ones, parity bit will be 1. So this will be the last will be the parity bit. Our parity bit will be set to 1 if the number of ones in even parity is odd. Okay. When it is received by the receiver, he checks for the parity bit. If there is 0, that receiver gets to know that the frame must have only even number of ones. Okay. Suppose if there is a change in the bit 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. I am a receiver. I have received this data. Now I can check with the parity bit whether it is odd or even. I know that it is even parity. That means where there is a parity bit 0, that means that frame must have only even number of ones. Okay. In first frame, the number of ones is not even, instead it has become odd. While it was sent by the sender, it was even. At the time the receiver receives that data, the frame has got odd number of ones. Okay. When the receiver checks this one, the receiver gets to know that the message has been corrupted and there is an error in the data that has been sent. So this data will be rejected by the receiver and an acknowledgement is sent to the sender specifying that there is an error in the message, and the sender will resend the same message once again. Okay. So this is even parity. Odd parity is contrary to the even. It also uses 0 and 1. In case of odd parity, if the number of ones is odd, then the parity bit value is set to 0. If it becomes even, then parity bit will be 1. If you take the same example, same frame 1 0 0 1, 1 0 1 0 and 1 1 1 0. If this is the original frame sent by the sender, if it is odd parity, what does it says is, if number of ones is odd, then parity bit will be 0. That means if you have 4 bits of frame, again you have to check for the number of ones. If it is even in odd parity, the parity bit value is 1. Here instead of 0, it will become 1. Okay. In the second frame also, number of ones is 2, the parity bit will be 1. Whereas in the third frame, the number of ones in this frame is 3, that means odd. The parity bit will be 0. So you'll get the data like this: 1 1 0 0 1, 1 1 0 1 0 and 0 1 1 1 0. Okay. The frame remains the same, only the parity bit value changes based on what type of parity we are following and how many ones are there. Okay. So this is with odd parity and this is with even parity. Okay. 0 1 0 0 1, 0 1 0 1 0 and 1 1 1 1 1 0. Okay. This can be used to detect the error by the receiver, as I have explained with the even parity. In odd parity also, if number of ones is changed one time or number of bit is changed in only one position, the parity check can detect the error. But one of the disadvantage is in parity check is if multiple times data is changed and the number of bits become equal to same, then parity check will not be able to recognize the error that has been generated. Like, for example, we have this odd parity where we have two ones in this frame. If one bit is changed and will become 1, number of bits will become, 1 bit will become 3. That means receiver can detect an error. Instead of that, if the frame becomes twice changed, like 1, 1, 0, 1, 1, 1, 0, 0, 1 and 1, 0, 1, 0, 1, 1, 0, 1, 1, 0. If the second frame changes like this, if 2 bits gets changed, instead of 1, 0, it has become 0, 1. But what is the problem here is, when the receiver method or technique receives and checks the number of ones, it will be even number only, even number of ones only. But it has been changed 2 times, 2 bits have been changed. But the restriction of parity bit is it cannot recognize how many bits are changed. It will check for only total number of bits or total number of ones. So if it is multiple bits are changed, the checksum or the parity bit method may not be able to recognize the error. This is one of the main disadvantage of the parity check method, where it cannot track how many times or how much bits have been changed in the data. Alright. Upon receiving the frame, the receiver counts the number of ones, and if there is change in total number of ones in a frame, the packet will be rejected or the entire data will be rejected, and the source has to resend the data. Okay. As I have said, the drawback of the parity check is it is suitable only for single bit error detection. If there is any change in only one bit, the error detection code will be able to recognize. If there is multiple bits changed, it may not be able to identify the error in the data. What is the solution for this is, we have the tabulation of parity bit generation. Here you can observe the equivalent decimal values from 0 to 15. Next we have messages with different data. Here, if it is odd parity, it will check for the number of ones. Okay. If number of ones is 0, parity is set to 1. That means it is even. Okay. Here, the number of ones is odd, so parity bit is set to 0, whereas in even it will set to 1. That means odd and even parity works in reverse manner. That means when odd is set to 1, even will be 0. When odd is set to 0, even will be 1. You have the tabulation of error detection in this. Alright. Next comes to the another method, that is generating a checksum. How do you generate a checksum? Is there any particular method to generate a checksum? Is data is divided into fixed size frames. It may be any error detection method or any kind of data transmission. The data is divided into fixed number of frames. Okay. And what does the sender will do is, he will add the segments using ones complement. He will add all the digits in the frame using the ones complement method, okay, to get the sum. Okay, it will generate a ones complement and it will make the sum of that. Suppose if we have 11010, it will generate the ones complement. You know about how to generate the ones complement. Change the ones to zeros and zeros to 1. 00101 it will become, and will generate a sum of this 11111. So this will be a sum. It then complements the sum to get the checksum. Again it will generate the ones complement for this, like 00000. So 2 times complement will be generated or complement will be calculated and is sent along with the data frame. This can be called as a checksum. This checksum will be sent along with the packet by the sender. What does the receiver will do now? Receiver adds the incoming segments, all the frames, along with the checksum using the ones complement. Okay, adds the incoming segments along with the checksum. Along with this 11010, it will get the checksum zeros. Okay, using ones complement arithmetic to get the sum and then complements it. So it will add it and complement the message so that he can, based on sum that has been received by the sender, the receiver will counter check with the sum value so that if there is any detection or if there is any change in the final product, final complemented product, he can assume that there is an error. If the result is 0, complement is 0, the received frames can be accepted. If the received sum is not 0, if it is non-zero value, it means there is a change in the data bits that has been received and the data will be discarded by the receiver. Okay? The sender has to retransmit the data for this. Another method that we can follow is cyclic redundancy check. What is this cyclic redundancy check is all about? Cyclic, as name indicates, cyclic redundancy check. Redundancy is repeating the same task. Cyclic is completing or implementing the same method again and again in the same manner, in a cyclic manner. Why it is called as the cyclic redundancy check. How does this cyclic redundancy check will detect the error is, as the checksum involves ones complement sum, this involves binary division. Okay. In the previous sessions, we have completed with the binary arithmetic, is it not? Division operation. Same division operation will be carried out on the data frames or the data packets or the data bits. How many number of bits are there? For that, a division method is implemented. If you want to divide something, you need a divisor, is it not? Without any divisor, you cannot divide anything. If you have a number 20, you need to have a divisor. It may be 2 or it may be 4 or it may be 5 or it may be 10, it may be 20, is it not? You need something to divide this number. In cyclic redundancy check, as I said, we follow a binary division method. Which will be the divisor here is, there will be a predetermined divisor, okay, which will be pre-agreemented divisor by both the sender and the receiver. Both has to know and both has to agree on the common divisor which can be used to perform a binary division on a data frame. Okay. These divisor, how does the processor will generate this divisor is using the polynomial concept. Using the polynomial concept, a divisor is generated and this divisor is going to perform a binary division on the data packets. Okay. What is the role of sender and the receiver in this is, sender will perform binary division of the data frame or the data bits using the generated divisor. When you divide something, you may get a remainder or you may not get a remainder. If there is remainder, it will be mentioned either 1. Since binary division results only in either 0 or 1, what are the possibilities of remainder is either 1 or 0. Possible values remainder that we can get is 1 or 0. This remainder is appended with the frame, data frame. The remainder is added. This remainder is generally called as cyclic redundancy check bits or CRC bits. What is these CRC bits are going to do is, it will help the receiver to identify if there is any receiver in the or if there is any remainder in the division operation or not. So, it is repeatedly done with each of the data frame. If you send 100 data frames over the network or over the internet, all the 100 frames has to be divided repeatedly with the same divisor. Divisor will be same repeatedly or cyclically. The divisor is going to divide the data frame. For this purpose, this method is named as the cyclic redundancy check. Okay. This CRC bit is appended at the end of the segment. Okay. What is the purpose of adding this remainder is, it will make the resulting data bits or unit will be exactly divisible by the divisor when it is received by the receiver, because both have agreed divisor. If it is, for example, if you take the value 20, if I am a sender and there is a receiver, we may both agree that divisor will be 2 or divisor may be 5. There must be a commonly agreed divisor. Otherwise, the remainder may change, is it not? If the sender uses 2 and receiver uses 5, remainder and quotient will be different, is it not? Remainder may be 0, or if I use 2 and the receiver uses 3, the remainder may be changed. For this, we have to agree on same divisor. Okay. When the receiver receives this data, what he will do is, he will divide the incoming data or incoming data frame by the same divisor that has been given by the sender. If there is no remainder, if you don't get any remainder, 0, the data is assumed to be correct. That means, if 20 is the data and the common divisor is 2, the remainder will be, quotient will be 10 and the remainder will be 0. If the data is changed, instead of 20, the receiver receives 21 or 23 or 25 or 24. If the data changes and the divisor is same, the quotient may get changed and also the remainder may also get changed. Okay. So, here the remainder will become 3 and the quotient will become 10. Quotient will be discarded, will not be considered. So, we will check with the binary number. If there is any change, the remainder will also change. When remainder becomes non-zero, that means there is a change in the original data received. In such a case, the data again will be rejected by the receiver. Okay, this is something about the error detection codes. Okay. Next is all about learning how to convert a binary coded decimal number between the decimal, binary as well as XS3. Okay. We have BCD code. BCD code is, even though it is binary code, it is not similar to the normal binary representation. Binary representation differs from the BCD, even though it uses binary. Again, XS3 differs from BCD as well as normal binary. The purpose is, we have the electronic devices. It may use the normal binary representation for processing and BCD for representing, like if you have a washing machine or if you have a microwave oven, what does the display uses is either the BCD or XS3, or it may use gray code. But while processing, the processor will use the normal binary representation. That means, like we convert from decimal to binary or from octal to binary, we have the necessity of converting a data in binary to BCD form, or data in BCD form to the binary, or there is a necessity of changing the decimal form to the BCD. How does these conversions are done? We have discussed about few of the conversions in the previous sessions, is it not? In the last session, we discussed about BCD. Now, we'll look at how does the conversion will be carried out between BCD and other number system. Okay. The first method is converting a binary representation or binary data to a BCD form. Okay. What are the steps that can be formed is, first is, you have to convert the given binary number to decimal. Okay. Once you convert this to decimal, the decimal number can be represented as BCD. If you take an example, okay, I'll take the value. Here is a binary number. This binary number must be converted to BCD. I'll have a question. Convert 11000101 to BCD. This is not in a BCD form, is it not? Now we have to convert this to BCD. What is the first method is converting binary number to decimal. How do you convert this? 1 into 2 plus 1 into 2 plus 1 into 2 plus 1 into 2. I'll skip these zeros. Okay. You'll have 1 into 2 to the power of 0, 1 into 2 to the power of 2, 3, 4, 5, 2 to the power of 5 and 2 to the power of 6. Okay. So, this is 64 plus 32 plus 4 plus 1. Okay. Now, the decimal form of this binary representation is 141. Okay. So, this decimal form must be converted to BCD. Now, we know about how do you represent BCD. Each digit in decimal will be represented using the BCD value. 4 digits, 8421. 1 can be represented as 0001, whereas 4 can be represented as 0100. And 1 again is 0001. Okay. Now, the answer will be for 1100101, the BCD form will be 0001 0100 0001. Okay. So, this is how you can convert a binary form of data representation to the binary coded decimal. It is binary, but it is a coded decimal. Okay. Now, the reverse procedure is, how do you convert the BCD representation to binary? Now, the step here is reverse of this, where first BCD is converted to decimal. Again, the decimal will be converted to the binary representation. If you have a look at an example, I will have a data here. This is the representation in BCD. What is the decimal representation of this is 1001 will represent 9, whereas 0010 will represent 2, and the 0100 will represent 4. Okay, this will become 924 or 924 with base 10. Now this 924 can be converted to binary, or if you take a simple example, 100 and 0001. So this will be 8 and 1. Okay, the decimal representation of this will be 81 to the base 10. Okay, this 81 can be converted to normal binary by dividing it by 2. It will be 1, 2 20 is a 40, 2 10s are 20, 2 5s are 10, 2 2s are 4, 2 1s are 2, 0 1. Okay, the binary equivalent of 1 0 0 0 0 0 1 will be 1 0 1 0 0 0 1. Okay, 1 0 1 0 0 0 1. Okay, so this will be the binary equivalent of this BCD. Okay, this is one representation. Now we have other representation from BCD to XS3. Suppose you want to convert the representation from BCD to XS3. What are the steps you can follow is, first step here is convert BCD to decimal. What you have to do is converting the BCD to decimal. After converting it to decimal, add a decimal 3 to this current decimal number and convert into binary to get an XS3 code. Okay, if you take an example 0011 100. So if this is the example, you can convert it into decimal. 0011 will represent 3 and 100 will represent 8. That means decimal value is 38 to the base 10. For this 38, add 3. Okay, this will be 3. 41 will be the equivalent for XS3. Now, what you have to do is convert the 41 into the normal binary. Now we have the XS3 equivalent of BCD that is 0 0 1 1 1 0 0 0 can be represented as 1 0 1 0 0 1. This is a BCD form, whereas this is an XS3 form. Now the reverse of this is XS3 to BCD conversion. Okay, what you have to do is subtract 0 0 1 1. Okay, 0 0 1 1 is the decimal equivalent or binary equivalent of decimal number 3, is it not? 0 0 1 1 from each 4 bit of XS3. Okay, if you have 8 bits, from 4 bits of XS3 you have to subtract 0 0 1 1, which will generate you the BCD. Or as I said in the last session, how do you generate XS3 from BCD is by adding a equivalent of 0 0 1 1 or adding 0 0 1 1 or decimal 3 to the BCD. You will get XS3. Now we have added to generate an XS3. From XS3 to BCD, you have to subtract 0 0 1 1. Suppose if you use a value here, have this value. Now I have, this is in XS3 form. Now I have to convert this to BCD. Okay, how can you do this is subtract each of this 0 0 1 1 from this value. Okay, now we have to subtract 0 0 1 1 from 0 0 1 1. Okay, this is all zeros. Now subtract 1 0 0 1 or subtract 0 0 1 1 from 1 0 0 1. Subtraction will be 1 minus 1 0. We have 0 here. What we have to do? Take a borrow 1 from this. Again, this position doesn't have any value. Take a borrow of 1 from here. This will become 1 0. If you take this, this will become 1 0. Okay. This will be 1. Here 1 remains. 1 minus 0 is 1. You don't have any value here. This will be 0. Alright. How do you represent now? This XS3 is 1 0 0 1 0 0 1 1 can be represented as 0 1 1 0 0 0 0 0. This is XS3 form and this is BCD form. Okay. This is all about BCD conversion. The next thing that we can discuss is about the fixed and the floating point numbers. How do you represent the numbers in fixed point as well as the floating point? Okay. Usually, the digital computer uses the binary representation as I have explained in previous sessions, which will be used to represent any type of information in the computers. It may be symbol, it may be characters, it may be numbers, or it may be any instruction that you are going to give, like double clicking on mouse or right button clicking, left button clicking, or moving of the mouse on the desktop, or selecting any folder or deleting something. Whatever you do in computer will all be stored or processed as binary numbers, is it not? So, even alphanumeric characters, alphabets also represented using only the binary bits, that is alphanumeric codes. Okay. This digital representation is easier to design as well as storage will be easy. There will be accuracy and precision in the binary form of data. Okay. In this representation, we have two types. One is fixed point representation. What you mean by fixed point is it has fixed number of bits. There will be no floating numbers. There will be a fixed number of bits for the integer part. Okay, as you know, in any number or a number, you can have a floating point and the integer part and the decimal part. Is it not? Even though you don't have any decimal part, you can represent the 0 like 24.0, or this can be represented simply as 24. Both the representations are correct, is it not? If I represent it as 24.0, you cannot say that it is wrong. Okay. Usually the number representation will have the integer part as well as the fractional part. What is the representation of fixed point representation is? Here in fixed point, both the integer part as well as the fractional part will have fixed number of bits. This representation will allow only certain bits to be fixed for storing the data. Okay. How many data you may have? Only fixed number of bits will be stored in this type of representation. Okay. For example, if we have fixed point representation from 11111.fff, that is in hexadecimal, you can store the minimum value of 0000 to 0001, the last one, to the maximum value of this. Okay. You cannot store 98890.980 010. You cannot store because it has only fixed number of bits. Only 4 bits are fixed for integer part as well as fractional part. Okay. Since it is a bit number of bits are fixed in a fixed point representation, it has been named like that. Okay. There are usually 3 parts in a fixed part representation. Okay. In this also fixed point, we have unsigned fixed point. That means you don't have any positive or negative sign prefixed with the number. You have only the numbers, which is called as the unsigned fixed point. In unsigned fixed point, we have the integer part and the fractional part, which are separated by a dot or a period. Okay. So we have unsigned fixed point. What happens if you have a signed fixed point? That means representing a sign bit, plus or minus. In this, one bit is represented for sign, other parts for integer, and third one is fractional part. Okay. So we have 3 parts in unsigned numbers: signed fixed point, sign, integer and fraction, whereas unsigned fixed point number will have only the integer as well as the fractional part. If we have limited number of bits, what is the benefit of having fractional fixed point representation is the operating method and other calculating or processing will be easier if you have fixed point representation. Suppose if it is a floating point, that means you have a floating point part in the number. That means you can have any number of bits in the number. Okay. This is where you don't have any fixed value or fixed number of bits for the integer part or the fractional part. You can have a varying number of bits. You can store any number of bits, but there will be a limit for that, but it will not be fixed. You can either start from 0 to 9999 until the maximum number of memory location it can occupy. Okay, it doesn't have the fixed bits. Instead, it receives or reserves a certain number of bits for the number. Okay, it is not fixed for this much only. You cannot use the number beyond that. You can use any number of data, but you will have a reserved number of memory locations that will be given for the number, okay, where it is called as the mantissa or significant. Okay, it will have a mantissa part where you can add extra bits to your number. Okay, and a certain of number of bits to say where within that number of decimal bits. How much decimal bits it can occupy will specified by the mantissa part. Okay. Then in the floating point representation, there will be two parts. One is this example, this representation we have the sign bit. Usually floating point will reserve a bit for sign bit, an exponent as well as a mantissa. Okay. Here the first part represents sign bit and the second part is position of the decimal or the binary value where the bit is placed, and third one is the mantissa which represents the fractional part. Okay. Main difference between fixed and floating point representation is fixed point representation has maximum values. Only you can reach up to that. You cannot move beyond that. But in fractional part, it will allow you to have more number of representation and varying number of bits. Okay, you cannot say, suppose if you have 110101 and the bits reserved in this floating point is, suppose if you have reserved 9999 or you have reserved 5 integer part, 5 bits for integer part and 5 bits for fractional part, you can have 110.101. You can represent only 3 bits. 110.101. Okay, floating point doesn't bother about how many number of bits you have occupied. But in fixed point, if you use the same value and has reserved same 5 bits, what it will do, if I store 110101, remaining bits will be filled with the zeros. It will not allow you to store only fewer bits, lesser bits. Okay, fixed. You have to fill up all the 5 bits in the number. But floating point allows you with this flexibility to have varying number of bit representation in a number. Okay. So this is about the fixed point and the floating point representation. Thank you.